Welcome to the very first Meeting C++ student showcase, which is fantastic because we have so many students presenting today. And this is a program. 8 o'clock was a plan, but this is the first time and it's a lot of new people here. And so very, very nice to see that actually we're ready already. And it's great to see this program. It's so fantastic. And someone already asked if these are all students, because those topics, they're interesting. And do students do these interesting things? Yes, they do. We are going to hear about those topics from the students. There's another program point coming up where we're going to hear from someone else about teaching with C++. And that's Helmut. And let's talk about first how we got here. Also, dear students, welcome to the C++ community. That's something I want to say. That's really nice to see and hear from new folks in the community. You basically have now the starter set to start speaking if you want to. There's a ton of universities which have students, and so it's a super way to get some of those students potentially kick off their speaking careers here. So there's C++ conferences all over the world, and if you want to travel there, like to Berlin, to my own conference, and speak, that'd be an option by next year. CPPCon actually is starting to send out the acceptance notifications while I closed later and already have the program out. And also, dear professors, there's a group of C++ professors. I've been talking about this too. Thank you for your feedback very much. Also, there will be more professors because I know that I need to grow the group, but I think I have a slide for that. Yes, so these are the people teaching C++ at universities. So this started actually was Helmut Lavax from University of Vienna. And this goes kind of back to last year when I've met him at the conference, but also prior to that, I already met him for recording online talks, and some of those online talks were his students, and that kind of got us talking. And so kind of this idea was born between the two of us to get this rolling. Further input then came from Boguslav Stiganek and Petrus Roy. Petrus, hey Petrus, I think you're in the audience. I don't know about Boguslav, but he probably is. And I've been expanding the network to Konsain and Tom Tesh. I hope I got those names right. But anyways, also I've realized that Bjarne is a professor, and I've talked to him about it, and he really likes the idea. And maybe at some point we somehow have him in this also integrate, because he's a professor, he's taught for years. Another idea I have, so goals. I do want to expand the network. So right now with Bjarne, I think it's 6, and maybe I think I forgot a professor, so it's actually 7 already. So if I have 10 to 15 professors, I might also could do like a regular C++ professor / teaching panel. The event plans are kind of, I'm very happy that today is so successful. We have 6 students doing great talks. And the other thing I really like about it is not a lot of work for everyone involved. And for everyone doing anything here, it's a win-win situation, right? And we have like the students, we have the professors, we have myself, which I have a little bit of work to do, I realized today. And I don't know if we're going to do this as a seasonal thing, maybe not so much in summer, but like, later, or if we do this like every 2 or 3 months, because some of the professors already told me that they have potentially like 100 folks which could give a lightning talk or present like their project here in this format. And so if we do this every 2 months, we could like have a full evening of students, and very international. Today, I think we have most people from Vienna. Also, like, they had the longest part of having Helmut here, and Helmut already, is also doing a lot of work with the students in this direction. And I think that a lot of people, a lot of C++ professors might be able to learn something from him. So let's start today with a short presentation by Helmut himself, Helmut Lavax, about teaching C++ at the University of Vienna. And for that, I need to switch the slides. All right, we're ready to go. Helmut?
Thank you very much, Jens. My name is Helmut Lavic. I'm professor for computer science at the University of Vienna. And as Jens already introduced, I will talk about how we use C++ in teaching at the University of Vienna. And I will talk about how we teach the programming language itself, and how I make use of it in all the theses and that are created by the students, and how I mentor them, and what kind of topics we do. I come from the University of Vienna, Faculty of Computer Science, and I had a research group called Education, Didactics, and Entertainment Computing. In short, Eden, and my part is the entertainment computing part. So I focus on entertainment computing, a couple of stats about the university itself and computer science. Our university is quite old, was founded in 1965. We have roughly 11,000 staff, 87,000 students. We're a top 100 university. And we teach computer science in bachelor and master programs, bachelor lasting 3 years, master 2 years. And of course, in the bachelor, especially, we have introductory courses on programming. I will talk about them shortly. And mainly, they really revolve about C++. So there's a big chunk on C++. It's not only theory of programming, algorithms, how to represent data, and all those things, but then you really get into learning C++ as deeply as possible, but also then contrasting it, for instance, with Java, which is, of course, as we know, very similar. But the other big chunk that can be used for teaching C++ and other languages, of course, is when students actually work on their thesis. And in the bachelor program, at the very end of the study, students are supposed to create a thesis. And for the bachelor's program, they have about 1 semester, and the size should be about 25 to 30 pages. So it's rather a smaller thing. You can do it in 1 semester, but it still should be, of course, have good quality. And in the master's program, we have at the end of the master's program, we have a couple of lectures on just focusing on creating the thesis. And there, the thesis should be much larger. So it should be really substantial. You should devote a lot of time on this, implement a lot of stuff, and also have substantial scientific results, actually. Now, when we teach C++ at the bachelor level, we have 2 lectures consecutively, each of them having 6 ECTS. Usually, we have roughly between 200 and 350 students, depending on if it's in summer or winter. So that's a lot of students that we have to teach. So we have one frontal lecture where we just present the material. I'm not involved in this. I'm just telling what my colleagues are actually doing. And besides the lecture, there is then this practical course where students are supposed to create programming in much smaller groups, of course, so they can be mentored accordingly. And of course, they would learn in these programming classes the usual stuff. Of course, in programming 1, they would learn all the basics, the loops and classes, and even templates, as far as I've understood. And so really the basic stuff of C++, whereas in programming 2, of course, then they go much deeper, and then you get to stuff like smart pointers and SDL containers and algorithms, all the stuff that makes your life easier and that you need to know, actually. Now, teaching C++, as you can imagine, to students who have never heard of that is hard and is very difficult. And we see actually that students struggle with that. So we cannot say that after the lectures, they are actually perfect programmers. Some are, but they are more the exception, as far as I've heard from my colleagues. I asked them. But mostly we see that they struggle a lot in order to not only grasp the theory, but then, of course, implement the theory in practical programs. And so for that, I think that the time that the students have is much too short. So for grasping all of these concepts, you need actually years to focus on that. So it's a bit overwhelming. And my colleagues told me that they're kind of reworking now and kind of simplifying stuff, taking complexity out, so that what you actually see and learn can actually be contained in your brain. So you can take it in and really understand stuff. So simplify. So I think that's one of the big lessons. Here are a couple of teaching sources that we use. I think they're not surprising. Of course, Scott Myers is a staple. Professor Strostrup, of course, Herb Sutter. These are the big names and their books. And of course, we use them for teaching C++. And my students, they know more or less better than I do when they went through the bachelor, what is actually happening in these lectures. Now, my part is actually much later when the study ends. And they are now doing a thesis, and they want to work on a specific topic. And so they come to me, and then I have a big list of topics. You can actually see them online. So it's just follow this URL, and you can see all the topics currently available. And for me, a topic must be really interesting. It should be a unique idea. You should try to solve a real problem. So when you go through the world and you think about what's not working, of course, as a computer scientist, you try to find a solution with a computer in order to improve the situation. And of course, I really want to have a thesis that contain extensive implementation parts. So it's not just writing text. It's really you have to implement something. And that should be a substantial work. It should be hundreds or thousands of lines of code that actually works and that solves this problem. You can show it. You should know your theory, and you should be able to implement the theory in practice. And once you have all of this, the time you do that, I think you get more into the details of C++ and learn how to make best use of the language. There are a couple of formal requirements and maybe much more. I really, my big wish is when it comes out, when it's finished, it should be of such a quality that you can actually publish it at a conference. It could be a peer-reviewed scientific conference or in a forum like this, Meeting C++, for instance, or CPPCom or something like that, like an industry conference. We published a lot of talks at Vulcanized, for instance, in the last years. So I really want to have a very, very good quality. And my students know that I will not stop until the thesis really looks perfect. Of course, it must be a scientific work. You should have proper research questions, hypotheses, and carry out experiments, come up with good statistical induction in order to prove that. And here are a couple of topics that I'm focusing on because it's entertainment computing. It's more focused on games, gaming technologies. Some students are more in the design. They might create a game, for instance, a serious game. But more and more, we have students who are actually focusing on the very technical things, on game engine technologies, on the Vulkan API, Slang shader language, making use of GPUs and so on. And currently, I'm actually mentoring about 50 theses, so that's a lot. And so it takes a lot of time that I gladly invest in order to have a good quality output. Now, as a teaching resource, I actually started the Vienna projects on my GitHub. If you go there, you can find a couple of repositories there. And what I did was I tried to implement myself a lot of stuff like a physics engine, a Vulkan game engine, coroutines based job systems, and so on, a type list library for C++, in order to also to be sure that I understand what's going on, how these things work. And all of these projects that you can see actually are C++. So this is pure C++. And I try to implement them first myself. And then, of course, students might take over, might change it. Some of these projects have been initiated by students. I wasn't really involved in that, but mostly I am. So this is a very important resource for teaching. Already you have a lot of C++ code that hopefully works, that is well structured, simple. it should not be too complex in order to be able to understand what's going on and convey an interesting idea in the entertainment computing world. But still, it should be C++. A lot, and most of the time it is. So here you see the Vienna physics engine and how I simulate all of these objects. And one of the talks today will actually be around the geometry and collision library that takes out a part of that and tries to implement it in a good way, because when I implemented it, it was probably not that good implemented. It just worked. So that was the mess thing. And now it's time to actually make it in good and well-structured code. I do this currently. So this is my side project I'm currently working on. This is my AI loop. Whoever's interested, drop me a line. This is simply a tool where you have a controller and a worker. And currently you see it's because it's now, this is a snapshot from an hour ago. It's working on the physics engine. It's trying to restructure the physics engine. And you have a controller and a worker. Usually I use Opus as a controller and Codex as a worker, but I ran out of tokens. So this really is eating up my tokens. And this is really working on my C++ repo and restructuring the code. And the controller makes the plan and the worker carries out, and they are connected with a database and with a message queue. And so it goes round and round, and gradually they are eating up all the tokens. So here we have already to date, we had 550 tasks that was sent to the worker and then coming back. So this is a tool that I also want to, at some place, when it is really, really polished and so on, I want to give to my students. And finally, a couple of links. If you're interested, we have my homepage and the topics that I was talking about, lots of thesis topics that my students are working on. We have showcases where you can see past thesis and some video, maybe an occasional video. But you mainly see the finished thesis, okay? So you can download the bachelor and master thesis. And here we have a couple of presentations. Most notably, in the last years, we had a couple of presentations at the Vulcanize conference, which is an industry conference about the Vulkan API. It's a C API, but there is a C++ binding that I will introduce in the teaching in the future. And of course, as Jens mentioned, we had a talk at Meeting C++ with two of my students, and these were actually bachelor thesis. So they worked on a specific part of my game job system and make it parallel and make it debuggable and things like that. So very, very nice work, pure C++, and we had a really nice experience in going to Meeting C++ in 2025. It was a huge event and really, really interesting. Yeah, and finally, I had also a talk at CPPCon 2021 about that. Yeah, if you're interested in any of these projects or just watch them, download them, drop me a line, whatever. Yeah, that's it. Thank you.
I should unmute myself. So thank you, Helmut. Very interesting what you showed there about teaching C++ in Vienna. And so let's continue with the program. And yeah, so we heard about the teaching part now, and we're getting started now. I just quickly want to say these are lightning talks, so that is basically the concept. No questions during the sessions, but we are hosting like a panel-like thing for questions for everyone at the end. And the time slot is up to 15 minutes, and if if 15 minutes in your time zone is a bit longer than it's in mine, that's fine. Because we're online, and if someone probably is not going to take 15 minutes and someone goes like 17 minutes, it's evens the things out, and we're here to hear from the content, and I don't want to tell students or everyone else presenting here to hurry up, and so we'll find out how things work. Also, for students, you don't have to present 15 minutes, okay? If it's 5 minutes, if it's 10 minutes, it's already fine. And with that, let's get started. And so let me set this up. So by the way, that's my work, to set people up, and then I'll tell you to start, okay?
Yeah, so let's get started. Thank you for this opportunity to talk about my project. My name is Fabian Haslar, and I did a bachelor's thesis where the project was a collision detection library for games. It was obviously written in C++, and the thesis was supervised by Professor Helmut Lavac, and it is called the Vienna Game Geometry Library. I'm from the University of Vienna, and I am currently doing the bachelor there at the Faculty of Computer Science. So, okay, I hope. Okay. So, what is the problem I try to address? You need collision detection for games, obviously, how objects are colliding and whatnot. And what do you use for that? There are a plethora of possibilities you could use. You could use a physics engine or a small physics solver. Probably all of you are familiar with Unreal Engine, which includes its own physics and stuff. And yeah, my project tries to address a part of that. The Vienna Game Geometry Library, short VGeo, tries to do pure collision detection. So only the calculations on how objects are colliding and not solving or responding to them. That would be a full physics engine. And it's part of the Vienna projects, which Professor Lavac already talked about. You can find it on his GitHub, where there is also the Vienna Vulkan engine, physics engine, and a bunch of other projects. Just quickly, the math library I used for this is Terathon Math Library. It's by Eric Langell. This is based on a geometric algebra model, which he developed. Not only him, but plenty of other people. And he did a library on this model, and this was interesting for my project because it's way too broad to talk about this in depth here, but just a quick info that there are obviously 3D vectors and 4D matrices, so the standard operations you'd expect in game engine development. And there's also a wedge product and anti-wedge product, which are just operations to join geometric models or combine them. Yeah, that's all I'm going to talk about that. If you really are interested in this, I'd recommend you check out his work. So my library offers currently in its state 4 shapes: an axis-aligned box, which offers no rotation, a capsule, a polytope, which can be any set of points and faces, and a sphere. And the way I implemented this is through a C++ concept. So the required functions that those need to implement are listed here. So compute bounding volume. This is templated on a bounding volume, which is also a concept. Centroid and support, which is used for the calculations, and intersect ray for providing also not only collisions, but shooting a ray into the scene, so ray casting and that. And to solve the problem with polytopes, because on the left you can see an object I loaded into the library, the Utah teapot, and this is too complex and expensive and honestly not worth it to do collision detection with this in the context of games. So I built a convex hull builder, which the result of that you can see on the right side, how the teapot got transformed. And for this I used a quick hull algorithm. Okay, so creating the system. So you just everything is managed internally, and you can change some stuff at creation if you want to go deeper. But basically, you just create the collision system, which takes a template of the broad face algorithm you want to use, which is selected by default. So if you don't want to do anything, this is how you create it. And then you define and add your shapes. So here you can see you define a sphere with a radius. There is a define function for every shape, and it takes the respective parameters. And you get a geometry handle, and this geometry handle is then used through the add function of the collision system and to actually instantiate it. And this yields instance handle. Yeah, and to build, I also provided two CMake options, which is actually double precision to switch from float to double, and with Vulkan, because right now it's not implemented. There are only Vulkan stubs, but in the future it is planned to include a GPU path to accelerate some stuff. And these are the handles. So the geometry handles, they are uint64 types, and they use bit shifting and masking internally, and they are used to identify shapes in a basically just a slot map with an index, a generation, and the geometry handle additionally has a type, which is used to identify the shape type internally, and the instance handle is the same, just without the type. And on the right, you can see how an example would look for both of them. So in the geometry, you see the 3 is the type, then the generation, then the index. These are the queries you can do with the library currently. You can query all, which just calculates every possible collision there is currently and gives you the result. You can also just query a pair, so you provide two instance handles and it gives you the collision of those two objects if there is one. And then also a quality of life function is query overlap, which is just the same as query pair, but just as a Boolean query. And you can also cast array into the scene with an origin and then direction. And the results of those queries you can see here. So query all provides a vector with all collision pairs, and the collision pair contains the two handles that are part of the collision and a shape contact, which contains a normal, the depth of the collision, and two witness points, which you can see on the right. These are two boxes colliding, and the two blue points are the witness points, and the separation vector, which would be used to separate those two. And from the raycasting, you also have a ray hit, which is very similar. You get the instance handle and a position of the ray hit, the normal, and the distance along the ray where it hit. Coming back to the broad faces, so if you want to choose which one to use, you can do so via the templates internally. So here you can see the general broad faces, which are also a concept, so they need to provide the same functions again. Index grid and sweep and prune are the basic general broad faces, with index grid also taking a float for the cell size. So this is basically just a 3D grid where the shapes get populated, and it only checks against its neighbors. Sweep and prune, where they are put into axis-aligned bounding boxes and spread out with a min and max point along an axis. And then lastly, I also have a refinement of this broad broad phase concept, which is a broad phase with a bounding volume. And this is currently a bounding volume hierarchy and brute force. Brute force was initially just added for testing purposes, but I kept it for comparing results, which was interesting. And bounding volume currently is only AAPB, so this will probably be extended to support more of them. And for the narrow phase, there is a GJK and EPA collision detection algorithm which are implemented for general fallback. So every time a polytope is part of a collision, this gets used. And in other cases, there are specializations which capsule sphere and sphere and capsule are provided. And on the right, you can see some tests I did, which means when you can use the sphere, it's obviously much more efficient. And I'll also show you an evaluation. This is a testing I did with just querying all collisions. I did it up to 10,000 instances, and you can see actually here that at 10,000 instances, I tested this with spheres on my PC with about 25,000 collisions. It takes about 10 milliseconds. So if you look at that in regards to the frame budget of 60 FPS, it's about 60% of that. And if you compare it to the brute force, which took 190 milliseconds, and brute force is just testing every shape against every other shape. Yeah. And now I'd like to show you a short demo I did with Raylib. Okay, so here you can see the shapes. This is, again, I visualized this with Raylib. And this is the box, the capsule, and the Utah teapot. This is the original model. This is the one I got from the convex hull builder. And you can move the shapes. This is all done. So the graphics is Raylib, but the calculations is all done by the Vienna geometry library. So you can move the objects. You can rotate them, you can scale them up and down. And here you can see the collision detection in action. So it's calculated on the fly. Again, the two witness points, the separating vector. And I'll quickly show you also the ray collision. So this is it. You press R to cast a ray, and it gives you each collision with the shape and the hit points and the hit normals. So concluding this, as I said, for future work, the reason I used concepts originally is because I knew in the future it would probably be extended, not by me, but additional bounding volumes. As I said, only an axis-aligned bounding box is currently available. More shapes, maybe more broad faces, and as I said, a GPU path with Vulkan to increase performance, and eventual integration, as Professor Hlavac said, into the Vienna Vulkan engine or this ecosystem. Yeah, that concludes my talk. Here you can see all the info again, and thank you so much for listening. And yeah.
Thank you. Let's get to my slides. Right. So, thank you, Fabian. I also need to tap to my slides now. Yeah, here we go. Thank you, Fabian. Really nice to hear about this, and let's go to the next session, which will be Alexander. I got to
So let me start then. Hello, everyone. My name is Alexander Polinsky, and today I'd like to present you my bachelor project called Slang Factory. So first of all, Slang is a modern shader language, and it's very flexible and suitable for many engines and renderers because it can compile shaders into any suitable type, for any engine or renderer. And so the main idea of the project is to generate the shader code programmatically in C++, then compile it through the Slang API, then extract the reflection information also thanks to the Slang API, and then use the generated shader in the renderer or an engine. So first of all, my motivation, So my motivation was the shader programming often contains a lot of repeated patterns. For example, vertex inputs, uniforms, varings, and fragments outputs. So they often follow similar structures. And also resource handling and shader interfaces can easily become an error prone if everything is hard-coded. And so I wanted to explore whether this process can be made more modular by generating shader code from structured input. And so the goal of the project is to build a modular shader factory in C++, and the system should accept the structured parameters, generate valid Slang shader code, then compile it to a suitable type, for example, SPIR-V, and then it also should extract the reflection information through the reflection API. And finally, in my project, I also wanted to demonstrate it somehow. And so that's why I've decided to make a renderer. So there is also a renderer that I made, which basically proves the concept that I've got. So a little bit more about Slang. So why I choose Slang? So I choose Slang because it's not only a shader language, but it's also provides useful APIs. So it has a compilation API, has a reflection API, and both of these APIs are working absolutely great. Compilation API compiles shaders to any types you need. The reflection API gets all the reflection data from the shader you need. So that's perfect. And so that's made the Slang language a very good fit to my project, because I wanted both. I wanted shader generation and I wanted shader reflection extraction in one workflow. And so in my current setup, I compile the shaders into SPIR-V, which is suitable for Vulkan because I have made a Vulkan renderer, so it works in Vulkan, and that's why for now I'm compiling everything, all shaders to SPIR-V. So now a little bit about the high-level architecture of my project. So this workflow starts with the shader request. So the shader request, basically it's something that describes what kind of shader should be generated. So whenever an engine or renderer needs some shader, just send the shader request, and it tells which shader it needs, with which parameters, etc. And then there is the Slang shader builder. So the Slang shader builder is basically a facade class. So it just orchestrate between all the classes, so between the Slang factory, compiler, extractor, etc. So the shader request goes to the Slang shader builder, to a facade class. Then what we have next, we have the Slang factory. Now the Slang factory generates the Slang source code. So the real Slang source code written, so it just generates a file with a valid Slang code. That's what the Slang factory does. Then after the Slang factory, we have the Slang compiler. Now the Slang compiler, it takes the generated Slang source code, which was provided by the Slang factory, and then compiles it into any suitable type. In my case, in SPIR-V. Then after the compilation part, we have the reflection extractor. Now the reflection extractor, it takes the reflection information and converts it into lightweight C++ structures. Yeah? And so at the end, we have the Vulkan renderer. Now the Vulkan renderer uses the generated SPIR-V, yeah, to create shader modules and render a demo scene, yeah, for example. So yeah, the important point is that the project is split into the small components, yeah, and each component has one clear responsibility. So there is no chaos in whole stuff, yeah. Now shader generation. So now I'd like to explain the shader generation step. The factory currently supports vertex and fragment shaders only. But yeah, so the input is not some handwritten shader code, but a structured C++ request. Yeah, as I've said previously, a shader request. So for example, the request can say, this shader needs a position input, maybe color inputs, UV coordinates, and should use MVP matrix and a base color. Yeah. So then from this information, the generator creates the common shader structures such as vertex inputs, fragment input, yeah, and it also creates all the required resources declarations. Yeah, for example, a constant buffer for the transformation matrix, and etc. Yeah, and then it generates the vertex entry points and the fragment entry points, and the result of that is one generated Slang module that contains the shader code required for the pipeline. Yeah? So that's what the generation looks like. Now the compilation pipeline. So after we've got our generated Slang code from Shader Factory, yeah, it goes to the compilation API. Yeah, so it goes to my compiler. So now here, after it was generated, the compilation begins. Yeah, and the compilation pipeline follows basically the Slang API workflow. Yeah, so the whole workflow that you can see here is written on the Slang compilation API documentations, and it's clearly follows that. Yeah, so how it works. Yeah? So first, the system creates a Slang session. Yeah? So that's the first thing that happens. Then it loads the generated module from a source string. Yeah, and this is important because the shader code does not need to exist as a manually written file on disk or somewhere. Yeah, so it loads module from the source string. Yeah, and this source string we've got from the Slang factory, so it was generated from the shader request. Yeah. Then the compiler finds the requested entry points, for example, the vertex shader entry point, yeah, and the fragment shader entry point. After that, the program is linked, and the compiler then produces the SPIR-V output. Yeah, so after the linking program part, we are getting the actual like compiled shader. In my case, it's SPIR-V. Yeah, and also at the same time, the system can obtain the program layout. Yeah, so you can see it's the last step of the workflow. It's the obtain program layout, and this program layout it's basically a basis for the reflection, and we will need that a bit later. Yeah, we will talk about this too. So this step turns the generated shader source code, yeah, into something Vulkan actually can use into SPIR-V, for example. Now the reflection part. So reflection is one of the most important parts of the project. And so the idea of the reflection is that after compilation, we can inspect the shader program and understand its interface. For example, we can see entry points, parameters, resources, uniform fields, yeah, and other layout information. And here I implemented two reflection-related components. The first one is the reflection dumper. I haven't talked about it, but so basically, what does the reflection dumper what does the reflection dumper actually does? Yeah, it just dumps out the reflection data right into the console. So this was just the first approach that I made with the reflection. Yeah, and basically it just made for debugging, inspection. So just dumps out the information. You can see it, inspect, and there you go. Now the second part of the whole reflection stuff is the reflection extractor. Now the reflection extractor, what it does, it takes the reflection information that we got from the reflection API, and then it converts it to lightweight C++ structures, yeah, into structs. And this is more useful for future engine integration, yeah, because an engine usually does not want to have some printed data, like here's data, good luck with that. No, so engine doesn't want this, yeah. So engine wants some structured data with which it can work, basically, yeah. So it wants structured data that can be used for resource binding, inspection, automatic setup later, all this stuff, yeah. And so then to show that the system actually works, yeah, and as a proof of concept, I created a small Vulkan renderer. So it uses the generated vertex and fragment shaders. Then it creates a graphic pipeline from the generated PRV, binds uniform buffers such as MVP base color, and then it renders a scene on a screen. And yeah, so this is also important because it's basically proves that the project is not just generating text, but actually producing shaders. Yeah, so the current result is basically working end-to-end prototype. So the whole chain already works, yeah? So we have generation, compilation, reflection, and also rendering, yeah? So, and we also render whole stuff that we made. And yeah, so for now, the project currently supports vertex and fragment shaders only. But yeah, in future, I plan to add more types and more varieties of shaders. Now, I'd like to show you a quick demo. In this demo, I basically want to show you how everything works. So here I just launched my my demo, my renderer demo. So the first demo scene is just a triangle, just pure vertex fragment triangle. Now we have a quad. So quad is already 2 triangles, yeah, and everything works just perfect. And then we have also the third demo scene, and that's the animated triangle. Now the animation is done purely on MVP metrics, yeah, so model view projection. So triangle stays the same in one place. The only thing that changes is basically the model view projection matrix. Yeah, it's also great because yeah, it shows that we can, we can work with parameters of shaders, yeah, so we can change the model view projection matrix, and then the model view projection matrix changes, and then it seems to us like the triangle is animated, but all the changed triangle stays in place, yeah, it just, the model view projection matrix changes. So yeah, and just a few more words about the current limitations and future work. So the current scope is intentionally limited, yeah, because I only had 1 semester, yeah, for this whole project. So right now it's intentionally limited, and I just focus on the vertex and fragment shaders. And also, yeah, I have a Vulkan render as a minimal demo, just for the proof of concept. But the future work could include support for more varieties of shaders, stronger integration with the rendering engine, and more automatic resource handling, yeah, so driven by reflection. And yeah, the conclusion. So to conclude, I developed a modular Slang-based shader factory in C++. Yeah, everything is written purely on C++. And the current prototype already validates the full workflow, yeah, from shader generation to actual rendering in Vulkan. So you can see it. And this gives a solid basis for future work, yeah, especially if the project is later extended toward more like engine-oriented shader generation, yeah, and integration. So it's already a very strong basis. And yeah, so I think that's it. thank you for your attention. And yeah, if you have any questions, you can contact me. And also have the GitHub link. And there is also a GitLab repository for my project. And it's also public, and you can look it there. I also made a very good README where you can read all the information in details. Thank you very much.
Thank you, Alexander. That was an interesting talk. And now let's...
So yeah, hi, my name is Miksch, and I'm also from the University of Vienna, where I write a bachelor thesis on neural rendering for subsurface scattering. The goal is to approximate the transmission part of a real-time rendering solution for subsurface scattering and see whether a neural shader can improve upon the performance while still keeping the visual quality. And furthermore, I want to see how different feature sets, network architecture, and sample count factor into performance and visual fidelity. How do I do that? I expanded upon an already existing renderer and added a data collection pipeline, trained a neural network, and implemented an inference as an alternative render path. After that, I evaluated the results. But first of all, what is subsurface scattering? Basically, it's light transport inside objects, which is especially important if you want to render material like skin or foliage, marble or wax. That is material that is emanating like a soft color bleeding, like partially translucent material. This concept has been tackled for some while now, first in offline rendering, then in real-time solutions. And the project or the solution I'm working on, or my project is building upon, is the NVIDIA RTX character renderer, which is open source on GitHub. And it has an implementation of a real-time rendering surface scattering solution by Zhang and Dion. That's the one half of the project. The other half is neural rendering. That is neural networks. That is multi-layered perceptrons, as they have been envisioned in already in the 50s. And especially the ability to approximate mathematical functions arbitrarily well, which have been proven in different degrees over the years, is especially promising for this employment. In graphics programming, it has been used mostly, or like first or most prominently, one could say, in upscaling and denoising, for example, DLSS. And in recent times, I mean, like very most recent, like the last years, more and more parts of the rendering pipeline have been substituted by neural networks, or at least try to substitute those parts, be it neural shaders, neural materials, or neural textures. I have the sources on the last slide. Let's look into the NVIDIA RTX character renderer, which I've already talked about. It implements the solution by Zhang, which basically combines two different approaches to subsurface scattering. It combines a diffusion profile and a ray trace part. And this ray trace part also has two different parts. One is a so-called boundary term, which basically is evaluating the light as if it would travel unscattered through the volume. And the other one, the other part, is the scattering term. And that is sampling a position on the way through the body and sampling a direction and evaluating the scattered ray. And in my project, I only try to approximate the second part of the second part, so to say. That is just what I said, the last, like the scattered ray evaluation. On the right side, you see the renderer. and we will see more of it soon. Just a quick overview over what I've did. I mean, first I constructed a feature set. That is, I used the parameters which also govern the analytic solution, like material parameters, volume geometry, ray tracing geometry, but then turned it into a suitable form for neural networks. For example, taking the logarithms, so to keep the variance in check, or taking the dot product of two vectors instead of all two vectors and all their parts. But I also tried alternative reduced feature sets which don't follow those guidelines actually, and those and try to minimize redundancy in the feature set, which I thought when thinking of universal approximators, one wouldn't put into a function parameters which you can even calculate inside the function out of the rest of the parameters. That's redundant. And if the function can do it, why shouldn't the neural network? And this actually proved pretty good, pretty successful, like just some days ago. I will show the results shortly. Yeah, then I created a data pipeline in the renderer. It uses a special interface by NVIDIA, which is kind of, I mean, one has to get into that as well. It's API agnostic, but leans more towards DirectX, as I can tell. And I mean, it's in C++ and HLSL as shading language. Usually Slang is preferred when it comes to neural rendering, but the character renderer uses HLSL, so I stick to that. And in the end, it doesn't matter that much syntactically. Yeah, I stored the feature set in a sample struct, wrote it into a buffer, copied the buffer, read it in the CPU, and then wrote the data into a CSV file, which I then used to train different networks in Python using PyTorch library, like the standard way. Different network architectures. I started with a rather small to medium-sized network with 2 hidden layers, then tried a bigger one, a tiny one, and then one with this before mentioned reduced feature set. And I also did try different sample sizes. I first trained only on 3.6 million samples, which I thought would be already enough, but it turns out the results improve a lot by increasing the sample size. Yeah, I use Atom Optimizer, mean squared loss as a loss function, and ReLU activation function. That's all very basic setup when it comes to neural networks. Then I built an inference path on the C++ HLSL side, meaning I reconstructed the neural networks there. I stored the weights in just regular C-style arrays, and to be able to calculate to run the networks inside the renderer. And then I implemented some add-ons for the UI so that I can switch between different architectures, and also to collect the data. I used an UI element. Here you can see like a short source code example of this kind of translation or transfer between Python, the Python side, and the renderer side. Like on the left side, you see in the upper left the neural network, and it becomes like, for example, the ReLU activation function basically is just the max function, and on the downside, like on the lower part, you see yeah, the tensor weights in Python, and I mean in the Jupyter Lab notebook, which runs Python, and on the right side the C-style arrays. Let's go into the evaluation. I mean, by the way, I have to apologize. The translation to the after uploading the slides, it got a bit mixed. Like the layout is a bit shaky, but I hope you can see it nonetheless. Yeah, the evaluation, it uses a scattering sample count of 8. On the far left, you see transmittance not enabled, like no transmittance. That means no light is hitting the ear from the back and using the translucency to emanate through the ear. Yeah, and the next one is the analytic solution, like which I use as the ground truth to compare against. That's why I put this green rectangle around it. And the FPS, like it's varying kind of like ±4 even, but it used to take some a bit higher range, one of the higher in the higher parameters. The next one is like the first try I did with the neural network with only 3.6 million samples. It was rather noisy. You can see it that well on the slides. It's just dark, but actually there was a lot of fluctuation. The next try was to make it bigger, which worked very well, very stable, a bit overshooting, a bit too bright. But the biggest problem was that the performance was very bad. Like it's only half as fast as the analytic solution, and that doesn't make sense then. And the next one was really well, also very stable. It's the smallish network again, but with 10 million samples more. And this resulted in a very stable image and mostly not distinguishable from the analytic solution, I'd say. However, what I thought is scattering sample count of 8, meaning you're taking 8 samples for each BSDF sample and averaging on the scattering evaluation. And that's actually rather high, at least for this year. And I thought it might be good for 8 samples, but it would be better if it worked also for smaller samples. And so it should be much faster. And so I tried a very tiny network, increased the sample size. And this, on the slide, it looks good, but actually it has some flickering and flash effects, which you will see in the video showcase in a short while. So this doesn't work out as well. But this aforementioned reduced feature set network worked very well. I thought not as stable as the version before, but in the video you also see no difference, I'd say. And it's even faster. So with these numbers on the slides, it's 34% more or less. When I first evaluated it, it was already even 40% faster. So let's have a short video showcase. I uploaded a video. So first the transmission part is off. And when we enable it, like on the left, you see like in the ear how the light goes through. That's the analytic solution. You see how if you change the light, like the visuals are different. You have 54 FPS. You see the frame rate on the upper left. Now this is the stable version, like the small to medium sized network, which I think which is like very comparable, which is not the case for the tiny one, which when you look at the eye, you see like these little flashes of light, even in parts which shouldn't matter that much. So this didn't work out as well. But this one with the reduced feature set, it improves a lot on the frame rate, and it's as stable as the other solution. And yeah, if you turn it off and on again, so here I have to run more tests, but at least up until now, you don't see much of a difference. Okay, so to conclude, performance gains were from 10 to 40% while keeping visual fidelity. I've already talked about the different networks and how they change. Like the larger network was lacking in performance. And especially the reduced feature set, which I rather recently tried, was very well and resulted in big gains with only minor visual loss. I mean, right now I don't see that much loss at all. And it's even faster already for 2 scattering samples. So I trained it on 8, having the good visual quality, but running faster. Of course, there are additional optimization possibilities. One could think about the attention architecture, for example. That might be a bit too much for this topic, but yeah. So thank you very much for your attention.
Thank you. That was interesting, and we are gonna go to the next presentation.
Perfect. So hi, welcome to Making a Game Engine with Godot feature using standard C++. My name is, thank you. So my name is Raphael. I'm a gamer at heart. I'm currently studying at Sherbrooke University. It's near Montreal in Quebec, Canada. Currently doing an internship at Audio-Kinetic. So for the context of our student project, we were a team of 4. We had average C++ knowledge, meaning like we knew what a destructor was, we knew like the rule of 3, how to handle pointers, but we didn't knew much about like smart pointers or like move semantics, and other things like that. So it was like a kind of a huge challenge for us. And we started, all teams started from the same baseline, I would say, which is called in French Petit Moteur 3D. I had to say it. In English, I would say PM3D. So PM3D, for short, to be short, it's like Learn OpenGL, if you know it, but for DirectX 11. So it guides us through making like our first cube, and then like putting a camera in the scene, things like that. So yep, and we had milestone to guide us throughout the semester, which the project duration was between 24 months, which is like pretty much the overall semester for us in Canada, at least in Quebec, I would say. And yeah, so we had between 3 and 4 months, but we also had other classes with the infamous AI class too. We had to use Windows DirectX 11, and we had to use a physics engine. Jolt was like highly recommended, and we all end up using it. And we had to make a racing game, essentially, using that small engine. So I'm just going to show like a very quick video, hoping that I still have time at the end for the rest of my presentation. So we can see here, we choose to make like a snowmobile. We thought it was super fun. There's light, shadow maps. You have UI on the bottom left. The camera can switch between a third person and a first person. We're going to see like in 1 second. That's pretty much it for the game. I'm going to focus more on the engine side. So sorry, PM3D, we kind of move away from you. Objects were having like too much responsibility in this architecture. It was hard to do like composition, and we just wanted to try something else, roll on thing. We're at university to learn and try new things, so why not? So we got inspired by Godot. Godot is a game engine, which is popular, I would say. At least on same level as like, maybe not on the same level, but as Unity, like on Unity and Unreal, and is infamous for its node and scene hierarchy. We implemented something very similar, which you're gonna see in a second. It's also popular for its. There's also a signal system, which is like pretty central to how you do gameplay programming in it. The signal system, is the observer pattern implementation of Godot. And Godot also have a Jolt integration, so I guess that's make another point similar to us. So for Godot's hierarchy, that's the real Godot hierarchy right there. That's a screenshot. That's like the latest version. So, I mean, there's way more objects, obviously, but I kind of filtered through it. So right now, on the top level, you can see you have a node, which is like your base object. You have then node 3D, which means like an object with a 3D position. And then you have collision object and all the children's, which are essentially physical object. Physical, when I mean physical, I mean physics as in physics, physics simulation, like body, like collisions, things like that. And then you have visual instance 3D, which is like for like visuals. So hierarchy is pretty similar, as I said. We have a node on top, node 3D for a 3D position, drawer, node drawer actually, but So we have a node drawer which handles all the DirectX 11 things, and And the hierarchy of each of these nodes down there, like of each of the leaf here, it goes even further. For example, Jar, we have like a model. We have another node model which loads a model and like makes the rendering on screen happening for the model. And we have Node Collider, which is responsible for interacting with our physics server, actually, which I'm going to show later. So for the node, each node has a pointer to its parent, except for the root node, it has a null pointer essentially. Each node is responsible for its children. So each a child node is necessarily a unique pointer, and it is contained inside a vector. And each node have a unique identifier, which is like very useful. We use it in many cases for example, the destruction. So our node interface goes like this. It's pretty standard. Like if you know typical game engines, you have like update 3D, updates like our loop, destroy. We're gonna talk about it a little bit later. And remove and attach is what we use to like link node together. So you may have seen like, hey, that's kind of weird. Like you're using like a R value reference right there to attach the nodes. Yeah, it's because we want to be very explicit about ownership when programming, at least in our framework that we made. So what I mean by that is every node in our system is a unique pointer, and if you want to like attach nodes together, you have to actually move it. So when you with the signature, what we are actually trying to say at least is, hey, I'm giving you the responsibility of the node that I'm giving you. So each parent node is responsible for its child node, and when it gets destroyed, it will destroy automatically all of its children node. So here, destroy actually respects RAII, which is difficult to say for me. It's not like a C thing where it's where we do manual memory management. It's really just marking the node for deletion for the next frame, essentially. And upon the next frame, we go through the sync tree through the nodes. And then when we know that the nodes must be destroyed, we just swap it with a null pointer, erase it, and let the unique pointer does its job. So it's very easy, like to both read the code, I would say, in some sense, and like understanding like making sure the objects are properly managed. So here for remove, I just want to say like we didn't know about algorithm when we started, and it was really great. We use it across all the code base right now. So here is just a find if. It's pretty simple, but hey, that's when you start using algorithm, that's where you might start to. And it was very nice for us to just like it was using that made our code more declarative and clear. So I'm going to move to the observer pattern here. So we have event signal. So it's not a signal, it's an event signal, right? It has a template parameter pack, if I say it right. So here params is the template parameter pack, and we params defines what are the params of the callback. So we have two aliases down there, which is we have a callback, which is essentially a standard function which takes some params. The params defined by the event signal. It was very useful for us to use a standard function. Like you could pass lambdas, you could pass, I don't know, man, a pointer to a function, member function. You could pass anything to a standard function. That was really great. Using signal, that's the alias for like an observer. So it's a pair between the node ID, which is unique, and a callback. So when a node connects to a signal, it gives its node ID and a callback. And we have a list of observers for the event signal. So here we can see like the logic for, we see the logic for the connection. So what would happen is like, you would take a signal, we would have a signal, for example, on it, we say on it.connect, pass the node, pass the callback, boom, that's it, observer pushback, that's where it happens. For the disconnection, again, pretty simple. I'm just gonna skip through it. And for emitting, that's where the magic of the pack happen. We just take the params and pass it, we just have to make sure that the signature is good, and then you can just call all the callbacks that were registered. I just want to insist on the fact that that template pack was very useful for us, because we have events, for example, when we change levels, we change from the main menu and the main level, or we have events, collisions, and other kinds of events. So not having to always define another event signal for each specific case was a huge gain for us. And also, the signals are like, they work hand in hand with the node system. So when a node is destroyed, the disconnection happens automatically, which is kind of nice. So for the Jolt integration, we really try to keep it as simple as possible. So I hope it will be clear to explain. So here we have the node collider. If you remember from the hierarchy, it's the one responsible to register a body, for example, to the physics server. A physics server is simply like a wrapper or facade, depending on like how you see it, to Jolt. And then the physics server registers collision to the mailbox, and then on update, when we are updating the game, the node collider consults the collisions from the mailbox. So here our mailbox is essentially a singleton. I'm just gonna skip through it for making sure we have time. Okay, so our physics server. So we see right on top the subsystem. That is what is wrapped by our physics system. Our physics servers. So the physics server wraps that subsystem. So right on top, we can see we have some data that is related to our needs. So we have bodies, we have raycast, we have bodies that we want to activate, bodies what we want to deactivate, things like that. And we have also like overrides, because in Jolt, you have like to configure, the subsystem, and when you're configuring it, you have to pass essentially like your implementation of certain classes. So here, for example, right at the bottom of the blue square, we have the contact listener. Each time there was a contact in the game, there was a callback in the contact listener that would get called, and from there we would register the collision to the mailbox. So the physics server like has a couple of methods for ease to use, so adding a force, adding an impulse, registering a body, launching a raycast, a couple of things like that we kind of wrap around our usage of Jolt. So here's the main the stepping function, which is like the update for the physics server. I thought it would be like kind of cool to see, like normally we don't see that kind of thing. So we can see like before we remove the body actually before stepping, and we add the body afterward. I hope that's a good way to do it. At least it worked for us. And we do our raycasting right there. I'm gonna talk a little bit about the raycasting, because there are a couple of C++ thingy that I thought was simple yet cool to talk about. So for example, just the optional right there, like in game engines, in games in general, there's tons of like situation where you actually don't know if you have the data or not. Like for example, here for the hit, we don't know if you actually got a hit. So I'm protecting myself from Raphael coding at 3 a.m. forgetting to check a bowl. Is the thing set? So now I have to check it with SCD optional. I can't, I have to take responsibility. And for the raycasting share ownership, we use actually a share pointer here. So that's one of the few instances actually where we use a share pointer. And the reason we do is because we want, let me rephrase it, like the hit is shared between the physics servers and the raycast. And the physics server may need the hit, and the raycast may need the hit too. But we don't know, like, for example, the physics server may not need the hit anymore before the raycast, or we don't know which is going to be the last owner, essentially, of the hit. And using a share pointer just solved that problem for us. It's very specific, and it makes the intent more clear when you don't overly use it, in my opinion. And we use make share, and I think you should use it if you're if you can. So we also have an editor, real quick. It does some pretty simple stuff, handle this transform, pausing the game, moving objects around, was pretty useful. But the editor, I just want to say, it has like a ton of functions that are like kind of similar to like metadata, I would say, almost. So there's a ton of code that you change that you didn't know you would need for the editor to work properly. So if you plan to do an editor, like really think through it before, I would say. And yeah, it was super useful. And being able to identify resource with a unique ID in the editor was like a lifesaver for us. And our main CPU hurdle, I gotta say it, was the building system. So if we knew about CMake more before starting out, that would have really helped us. Or about VC package too. There's a ton of things we didn't cover, like light shadow map, pop process, native UI using DirectX, camera and strategies. Like, of course, it's a game engine. I have 15 minutes and I've already got over. So in conclusion, we learned a lot. It was a great challenge. And C++ is very cool. And the usage of modern C++ really simplify our code. Thank you.
Thank you. That was really nice. Next one should be Dennis Gusti.
So my name is Denis Gusti. I'm studying at University of Vienna, and for my bachelor thesis, I am developing a Vienna traffic simulator. So when we have a big city and we have, for example, some kind of natural disaster or some kind of accident on some plant or some attack, we want to know how the traffic in the city, when the cars are evacuating from the city, how does it behave, like if you want to evacuate from the whole city or only from some part of the city. And that's what I was trying to research. So for my engine, I'm using C++, also with Vulkan library and Slang for shaders. So similar projects that model traffic are using like mostly CPUs or are like multi-threading, and I wanted to explore how does it perform with using compute shaders in Vulkan and GPUs. So it also supports like graphic GUI mode when you can play with and close open exits or change, so it reroutes dynamically. And also it is possible to just use like JSON input file to configure the scenario and then run it in batches without GUI. So you can explore only the results if you want to test some scenarios. And in results, we have like per minute statistics, how many cars are actually evacuated from the city, what is the flow through each exit of the city, and what is the speed, median speed, and other stuff. So it works like a scientific modeling tool. Yeah. So how does it actually work? I'm using a library in Python called OSMNX that takes the data from the OpenStreetMap, and then I'm preparing this data for the C++ main C++ application. So it creates a graph, directed graph, where each city is modeled like as two-side road with two edges, directed edges, and it precomputes precomputes the fastest route from the city initially, and also the main problem was that, for example, the places for the cars is not like open source data. It's nowhere to be found. So I try to evaluate where the cars are mostly concentrated in the cities, as they are concentrated on public parking slots, also in underground garages under the houses. And I try to evaluate how many cars are actually hidden on each side. And I use the area and for that, because it's very easy to calculate on the map. It's open source data. And then I am just using that library to put these cars to the to put these cars to the nearest edges, so they can spawn there. And also I try to validate this approach with population data of Vienna, for example, and then it was actually very similar to where the people live. So I think it's quite realistic. And yeah, so what I'm using for my model is, so the program works with compute pipeline that is necessary, and also if we use GUI, it also uses graphic pipeline. So for compute pipeline, it is like trying some optimizations, like it's trying to evaluate which cars are on this edge at this time. So if cars try to use the try to see each other, it does not it does not search the whole city, only this road. And for the physics, and the physics works like so each car is actually using this intelligent driver model, where it tries, so each car is like an object, and it tries to ride the most efficient way in the city. So it uses delta v to the next car, the distance to the next car, acceleration, the acceleration, and time to reach the next car. So it uses, so it changes its speed each, I think, 0.1 second. So it's like discrete time model, but it's very fine. And also to make the scenarios more realistic, I'm using congestion rerouting like in real world, because everybody will use like Google Maps, and it will automatically change the routes. So if there are a lot of cars on the street, it will give a penalty to the street, and it will reroute through the next route. And it's also done via rerouting is done via the multi-source Dijkstra. And then this data, so this data is done on CPU because it's faster, and then it is put to the GPU. Everything done in the C++ with priority queue. Yeah. So I tried. So my model uses 673,000 cars. So actually in Vienna there are 750, but as I said, it's not open source data where the cars are parked. So I tried to use area-based evaluation where the cars are, and it was actually quite close, less than 5% of difference. And I did not scale it to 750 because it would create unrealistic data in the parking lots and unrealistic congestion. So I think it's good enough. And yeah, actually I tried to model, and all the streets in my model is quite simple, and all streets are like one-liners. So the results are like the cars are the cars spent like 22 hours to fully evacuate the city, which I think is quite realistic, and the peak flow was 1,500 thousand cars per minute from the city. And maximal number of cars on the road was 400,000, and 400,000 were waiting. So here are actually the graphs that I got from my simulation. And as we see, when all the cars are starting to evacuate at the same time, they are actually very slow, and then if some number of cars is evacuating, the speed grows up. And also here we see the flow rate from the city, from all the exit nodes, and how many cars were at some time in the city, and how many cars did pass through certain exits, like top 5 exits. So I can actually show the, I think, how my program looks like. I need. So okay. So it uses like entry JSON file where we can put parameters like participations and files where we get the graph. That's how the program looks like. So as you see, you can start simulation, change the participation rate, or change speed. So we start the simulation, and we see that each car changes its color based on the speed, and we actually can choose each car and inspect what is the current speed of each car, and on which node is it, and what is the distance to the end of the node. And we can, based on the colors, we can understand where are the main congestions on the road, and yeah, like that's how the cars look when they get purple when they are got. Also, we can select like marquee selections, exit nodes that we want to close at any time, and the simulation will dynamically reroute in C++ the roads for all cars. And the maximal speed is actually 256 of real speed. So basically 1 2 minutes per second of real speed. And yeah, that's how it looks like. If there are a lot of cars, it tries to another route. You can also inspect the car during that also. Purple stuff is capacity, how many cars can spawn on the street, and it's very close to the actual population data of Vienna. So it's also very interesting. Yeah. And also we have some flow rates, dynamically created charts on the right that shows the cumulative number of evacuated cars and the flow rate. Yeah, and all the results are also saved to the result JSON, so it can also work like a scientific simulation without the GUI. We can just get the data from the JSON and everything. We can build graph from that and stuff and other stuff. So yeah, and we also have like average speed and other things. What is actually the future works that I plan to introduce in simulator is traffic lights data, because currently it's working like on each intersection there are stop signs, and the cars are stopping, and who is the first, then this car is going through the intersection. Also, in real life, not all cars start from the one time point. They are actually like departure time is Gaussian distributed, so I can implement that also in the future. Also, my model only uses like one line per direction if the street is two directional, but in real life there are also multiple lines on the road, and I would like to also support line changes and overtaking, so the throughput is bigger and the data is more like realistic because of that. Also, I want to add features like road closures, so we can also have scenarios when we want to close, when we have some incidents on the road, when everybody is evacuating. And also, I would like to add more fine-grained control of flows, like how many cars are going through each road or districts levels. So it would be more like it would be, you can more closely understand where the bottlenecks are, not only the exit nodes of the city. So yeah, so it is quite performant, I would say, because it can model in real life with GUI 700,000 cars, like each object. So I would say it's very performant, even with when we can dynamically route things. And it also can be extensible, quite extensible for the additional things, like I said, multi-roads or some other scenarios like paid roads or other stuff. So we can expand this engine. So yes, that's all. See.
Thank you very much. It already brings us to the next speaker. Thank you, Dennis. Very nice presentation.
Okay, so I will present my project, which is real-time 3D world generation. And what it basically does, it takes OpenStreetMap data and it converts it into a 3D world at real time, which can be explored in a game engine, and you can move the camera around and view various cities based on real data. So first I want to disclose the AI usage. I did use AI for consulting for new C++ features because I found it really helpful if, for instance, I would have an idea how I would make it, and I was a bit unsure if it was the most elegant or most up-to-date way to do it in C++. For instance, sometimes it's the standard library offers, for instance, something better to measure time than what one is used to, or something else. And I also used it for generating most of the textures for the project, and the 3D trees, the models were also AI generated. But moving forward, my project basically takes the Google Filament engine with CMake, and it basically does the world generation at real time. So it goes through various steps to achieve this, and to allow the world to be loaded, to have an arbitrary size of the world. So for instance, it can't load the entire world at once, so it loads only chunks, and when you move the camera, it loads other chunks and removes the others from the view, similar to some games that use this, like Minecraft or such. And the geometry of the buildings also generated from this data, so it basically extrudes it takes the outline of the building, and then it generates the triangles and the UV maps and everything it needs to make a 3D model out of it. And it allows basically two ways to do this. One is to just load a pre-downloaded .osm file, which is an OpenStreetMap XML file, or it can also stream this data. So it makes a request at the server from OpenStreetMap, downloads it, and then parses it and generates it. So it's compiled with Clang, because Filament only supports Clang as of now. And my project I've only successfully compiled it on Linux. It uses many packages, and the package management was probably one of the more demanding tasks to do, because on Linux you could have the packages from your package manager, but I thought it would be not so ideal for cross-platform compatibility, so I also integrated CPM, which is CMake project, CMake package manager, which basically downloads the required packages it needs, and it's only worked for 80% or so of the libraries. So for SDL or other libraries, I still had to use the integrated packages. So I will try to prove that. And my project basically has custom structs, which it stores the data in. So it loads from the ML file, it stores it in a struct, which basically represents this OpenStreetMap data. Then this data is converted with various classes, and they basically convert it into a format which basically contains in a struct which basically only contains the data that is relevant for rendering. So for instance, if in the original data there's the outline of the building, if it runs through the converter, it basically maps the coordinates to the in-game coordinates, and it also runs through the generator to generate the walls and everything. And yes, there are also lots of textures that are used. They are combined on various layers, and also various materials used. So I implemented classes for these, which basically use a map in the background. So for instance, if I request some texture with the file name, it basically takes that file name as a key for the map, and then it can search if it's already stored in that map, and then it can basically return that reference. Or if it's not found, it will basically load it on demand. And this works pretty well in my testing. And I also have a custom class which basically decides which chunks are loaded next. So it takes a radius around the user and basically computes this has to be loaded, this has to be loaded, and it adds it back to a vector, which includes as the futures of the threads that will generate this data. And yes, each type of object has a separate class. So building and roads and terrain and such, they all have a separate class which will contains the code how to generate this, because the data in OpenStreetMap is not as detailed as one would like for 3D rendering. So it basically has to guess some things, or has to basically take some data that's most likely to be reasonable for this kind. So here we have an example how it works. So it would, if this would be the game word, we have various chunks. And if the engine decides, okay, I want to present this chunk, it first computes the coordinates that will be needed for this chunk. And then it starts an SD async. It starts on thread, which will basically then do all of the processing it needs. So first it starts with a request at the OpenStreetMap API. It downloads that part. Then it has some XML data that it can use. This is then parsed and basically stored in the structs in the various. And these are then passed to the generators and to the converters. And these will return the renderable data. And then this data is added to the main thread because the engine only supports adding renderable data from one thread. So it has to go back to the main thread and it will then be added. And this whole process takes a few milliseconds, so it's not that long. So I would like to show the video now, if that's okay. So yes, here you can see how it loads. As the camera is moved, it generates new buildings, and every building has basically a random roof color and a random texture and a random color. So it basically combines some random values to make it increase the variety and to make it visually more appealing. And for the most part, these textures are just random guesses, so they are not really real, but it looks very convincing. But the road data and the outline of the building and how the trees are placed, everything is based on real data. And as you can see, it loads quite fast. And yeah, and it's basically supported for every city in the world, basically. So yes, so these are all the libraries that I used in this project. So it uses SDL for window handling, as already mentioned, Google Filament for the rendering. I made a custom XML parser with a Rapid XML, SDB image for texture loading, HTTP lib for loading of the data. And I also included a JSON library because our OpenStreetMap also allows 3D models to be linked to a building. And then it has metadata in JSON format, so I also had to include that. And logging, I have speed log, and for generation of the geometry and for the roof generation, which is a bit more complex, I used the Seagull library, which basically provides all the geometry functions that I need. Yeah, and this brings me to the conclusion. So as of now, a prototype is implemented, and my idea is basically to improve further on this, and it would also be probably used as a good basis for some games. So for instance, this could be used for a racing game where you have real streets, or maybe flight simulators use something similar. And yeah, as of now, the source code is not public, but yeah, okay. And yeah, this concludes my talk for now.
Thank you very much. That actually concludes. Wait a minute. Let me. So this actually concludes our lightning talks today, because Emmanuel is the last speaker. And if I tap back into my slides somehow. So thank you very much. We had 6 great presentations tonight. Actually 7, because Helmut also presented about teaching. So thanks to you all, and let's quickly see if we do actually get some questions. And for that, I will go back to a more panel-like question and basically add you all back. So don't forget to unmute yourself if you want to say something. Just generally, I really enjoyed tonight and seeing all the topics. The one thing I've learned is like the tool I use is like really not suited for doing this. It can do it, but I'm being creative in doing it. So the people creating this part of the software really didn't think about people scrolling through this thing. But anyways, it's been a great day for everyone here. I think. I hope you felt welcome. Let me see. So if you're on LinkedIn, just post your questions to the chat, and I'll put them on here. And if you're on Hubido, then just the Q&A panel, but no one has done that yet, and people. So yeah, let's see if we get any questions. See, Petrus is there, and Petrus Roy, one of our professors. Wonder if he has a question, but he actually says in the chat, "Thank you, everyone." And yes, that's. But generally, maybe my first question to you would be, how do you generally feel about working with C++? So if some of you want to just unmute yourself and answer this question.
So maybe I can talk something about it. I've been using C++ since the 1990s. So beginning of the 1990s, I started at the university using the Glockenspiel C++ compiler, for those who remember that. So these were ancient times, and there was just this thin layer of language and a little bit of library. And at the time, it was very easy to like grasp all of the basic ideas and these basic concepts and understand the library and so on. That has changed dramatically. Nowadays, we are confronted with an incredible amount of knowledge to gain and to learn. And C++ has really exploded in what it can give you and the ways you can implement stuff. And so this is a big challenge to teach the students the entirety of this universe. Because what would you want to leave out? What would you regard as not relevant? What is not usable? Everything is usable. Everything makes sense. But it's too much to be taught within even a year. Because newcomers who have never been confronted with that, even with basic programming algorithms, they have to develop the brains and the neurons, and that takes a lot of time. It takes years to understand all of these concepts. So I think for us, for the university, this is a big challenge. But I can say what I see at the end of the study, when years have passed by, when students had the time to think about all of this stuff, I think a lot of people are very, very good. And you have seen students today. And I actually also want to thank all of the students for the participation, because it's not so easy to throw yourself out here, present yourself to this audience. Like maybe it's the first time you've ever done that. It's a risk you're taking to present yourself, and I really want to thank you to be part of that. And I can also say with high certainty, all of the projects I've seen today are absolutely stunning and amazing. And you're a testament of what university can teach to students and what students can actually achieve within their studies. So I'm super proud of all of you. Like really big congratulations.
Yes. So since I run this show, I get to answer the real first question. Actually, some of you showed code, and I want to be nice to you, but so either I have to blame the professors, which is Helmut. Pointing fingers on camera is always difficult. It's never the finger on the direction you think it is. So what I just so my question and my question goes to every one of you, but especially I've noted this with Raphael, who I know who interfaces with Godot, which is not like something which Helmut came up with or which is like provided by university, but it is an external project. So how much of your code is dictated by the interfaces you need to use for your project, right? If you want to do something for Godot, you've got to use that. So
I mean, I can answer. We don't use Godot. Did I understand the question well? Like we don't interface with Godot. Like we kind of emulate in our own engine, like the how Godot works in a certain way. So like Godot exists on the on side, and like our engine exists on the other side. So we weren't limited. Like we had no limitation.
Okay.
It was amazing to have no limitation, but it was amazing yet. But you have a lot of responsibility too, right? Because you can shoot in yourself in the foot so hard. Yeah, but yeah. I hope does that answer the question well?
Yes, I just I wondered, like, I mean, I know Godot has a C++ part, and I wondered, are you using it? And also, I mean, it's the perfect part now to basically, ask Helmut about, because I know that his university has like a big collection of things which are implemented by students, and then it's probably then reused by students and just part of what he teaches. So, Helmut, just like, what is your thought about that? I think you're muted, Helmut.
So you mean about reusing code or interfaces? Or what was the question?
I mean, how much of the code a student writes is dictated by the libraries that they have to use to complete their task, right?
That's a good question. And the point is there are a couple of standard libraries that are very popular and give you a lot of functionality. Async was mentioned, SDL3 was mentioned, ImGUI was mentioned. So basically, these are you can find them in most projects. And so if you use these libraries, then of course the code that wraps around these libraries will always be the same and very comparable. And that also is a chance if you throw out projects that use this code, then students are confronted with that and immediately learn the relevant libraries. Otherwise, I really try not to use too many libraries in my project. So really, it doesn't make sense to reinvent the wheel. Like you have Async. Async can do everything. You can load assets like geometry and stuff for your games. It doesn't make sense to like reinvent the wheel, but don't include too many libraries, because where's the joy of programming when you like just stitch together all these libraries? And I think the real idea or the real art is to come up with topics where you could not find all of the functionality in the totality of libraries that are out there. So make a pick, have a topic that is relevant and that is not solved yet, and then pick the libraries that fit to that and build on top of them. But don't use too many libraries. So because then you have a lot of freedom to create your own software architecture. But as I said, there is a set of libraries. You'll find them everywhere. So the typical graphical user interface of ImGUI, it's in 99% of all the projects out there, and it's a good. I mean, there's a reason for that. It's really amazing. So
yeah, it's just. I mean, we don't do so much graphic programming. I think it's a new thing which we do now here at me, C++ with the students. And I see also like, this seems to be like a thing which is generally how C++ is taught. But I'm kind of also amazed that, this hasn't played so much a role so far in conferences, because, people that actually do things for a living with C++ don't do so much with that if they're not in the game industry or write simulations for science or simulating other things. But maybe just let's move on for a more general question on the for students. Now that you have experience with C++, what do you consider to be the fun part of coding in that language?
So I think about if I program in other languages, at the end of the day, it feels the same on a abstracted level, at least, because I'm only using it to get what I want. But in regards to C++, I think what I really enjoy are the STL containers and stuff, and this the code that C++ already provides. And in particular, also, I think it gets a bad rep, but pointers, which I didn't get to use much in my project, unfortunately. But yeah, I think once you understand pointers, and especially the modern C++ with smart pointers and all that stuff, is really great.
I mean, if I permit myself, I would say for me, it's like control. It's really cool to be able, like C++ doesn't hide you too much things, I think, compared like to Java, where you put like new everywhere and it just magically works. Now you have to really understand like your system, and if you want to know like, oh, how does that memory manage actually, like what happens, you can really deep dive, and that's what I love. I love to see the evolution. Like I know people like they complain about like C++ complexity or whatever, but like me, it feels like updating my game. It feels like it's a live service and it never stops. So it's pretty fun. I'm quite happy about it.
I can also answer this question. Like, I think the C++ is very fun because of the level of performance you can achieve thanks to the C++, and that's very great, and that's I think that's the thing that makes this language very interesting. I mean, of course, in order to achieve the high level of performance, you need to know this language very well, and it has a lot of challenges. So learning C++ is not that easy, but I mean, it pays off. Like if you can fully learn the C++, it will pay off. And also, like for me personally, this struggle to learn something difficult and get into it is also very interesting. So for me, it's like a challenge that I think every one of us accepts when tries to code something on C++. But yeah, that's great.
Very good. Any more takers? It's, by the way, fine if you don't want to answer any question. That's fine. And I know it's like also like my learning from tonight is like we have a lot of people here which are new to this, so we got to improve on that point a bit. So I also get just generally, you've all done great, and it's been really great so far. Actually, there's Alexander was just, I think, talking, and so there's actually a question about reflection for you. So does reflection not have runtime costs in your case?
So the reflection, I haven't tested this actually, how the reflection will affect my runtime costs. I mean, I guess it does, which will be logical, but I cannot answer this question like on 100% because I haven't tested it yet. Because my whole idea, so the whole goal of the project was both compilation and getting the reflection information. So it was from the start like that. It wasn't like I made the compilation of shader using the compilation API, and then I was like, okay, let's make the reflection. No. So it was both from the start. And so I developed it like both from the start. Yeah. So I had the compilation part, I had the reflection part, and yeah, so I just developed both of them. And I haven't yet tried to disable some stuff. I mean, theoretically, yes, you can leave the reflection. So you just don't need reflection. And basically, in my project now, I don't really use the reflection information. So I just provide the reflection information in structured C++ structs. Yeah, so it's C++ structured, all the reflection data, and it's ready to be used by an engine or a renderer, but I'm not using it actually because I'm not working with like an engine. So I just made a small renderer demo. Yeah, so I just made a small renderer on the Vulkan, that's it. So theoretically, yes, it's possible to get the reflection out and just do the compilation stuff. And it may affect the runtime. It may be better, but I haven't tested it yet. So that's the answer.
Nice. Thank you. Which I think brings us to the end. So if you're quick and post a question, I can ask it. I want to say another lesson learned is just keep your questions short. I'm limited in this space, and when people, there's for some people a certain tendency that they want to ask a question about a complex thing, and then they explain their question first, and then they ask the question, and then the question is too long. I cannot ask it because you basically put in 2 paragraphs, and so the question itself is not your question anymore. So keep yourself short. But yeah, so generally, I want to say thank you to the students who basically put in the main work of today. And I think we are coming to the part of the evening where we're closing down the event a little bit and just looking through things if we have another question. LinkedIn did not have a question this time. So generally, thank you, students, and it was nice to have you. So let's close out this event with a short talk with Helmut. And for that, I just, get all of the students the luxury to not be on stage. So you get a bit of your privacy back now. Thank you for being part of this. Really nice. And now it's just me and Helmut. So Helmut, thank you for just, inspiring this idea. And I think it worked very well for the first time. A few things to improve, and but that's not a surprise, right? And so, generally, what are your thoughts about what you saw today and what you do with C++?
I think that what I see with our students is really at the end of the studies, the students that make it, not all of the students actually reach the end point of their studies. We have a dropout rate, unfortunately, but those who make it, the niveau, the level is very high, and they really get into the stuff. And I'm very proud of what I see. It's not only one part; it's also, I think, it's a communication between student and mentor. That's also my message is: if you really want high quality, you have to put in the work as a professor, and the time for talking to the students and really reflecting. Okay, is this aligned with the vision? Are you going into the right direction? And giving feedback and really shaping in kind of where the thing is going. And then you can get results like that. I'm super proud of what I see. And I know, of course, having been in the C++ business for so many years, many decades, and have seen what C++ has become it is really difficult for newcomers to get into this. I think we heard one student saying they like to have a challenge, yes, and that's the great spirit is don't think about it as a burden. You know, I have to. Everything you learn of this mosaic of possibilities will increase your possibilities of doing stuff. So it adds to your toolbox. It can be anything. It can be templates. It can be lambdas. It can be templated lambdas. It can be recursive lambdas. Whatever. Once you understand them, you suddenly a world of possibilities opens. But of course, you really don't need them in any case. But so think about it as I learned something, and then suddenly I have so many options more than I had before. At least that's how I see it when I get into the new stuff that is out there in the new standards. I think, wow, amazing! I'm able to do this so easily, and before that it was like a nightmare to do that. And I think this is also the mindset that I would like to pass on to my students. Be curious about it. You know, C++ offers you a lot. It offers you everything. It it has been my go-to language for many decades. It never turned me down. I know it inside and out, and just stay curious. And the new standards are really mind-blowing. Of course, C++ 26 is absolutely amazing. What is coming out. So it's a complete game changer, and C++ nowadays looks completely different than it looked like 15 years ago. It's if you embrace the new stuff, it will change. It will be a game changer and up your game. That's what I want to communicate with my students. The beauty of that.
Yeah, I think one of the points where we're gonna get to, and tonight, unfortunately, we don't really have a good data point on it. It's like Raphael was the one student who isn't from your spot. So thanks to Petrus to sending this to his students. And I know from presenting from Canada at this point of time might be not as easy as for students today from Vienna. But I think we have a big chance to finally also kind of see what professors do. And so I wonder how much do C++ professors talk to each other? I really like what you do, and you send a lot of students to conferences, and I guess other professors probably do that too. Otherwise, they might get inspired by today. But generally, how's the exchange with professors?
Unfortunately, not much. There are reasons for that, because C++ itself is a tool. So there's no, I mean, some people do research on it, but basically we use it. But our research is actually somewhere else, you know. So when we do research, we are communicating with other professors who do a similar research on a similar topic. But C++ is just our go-to language to implement a research, you know. If you do language research, then I'm pretty sure that there's a community out there that is in communication with each other. But the topic of C++ itself is probably in a university setting, it's probably more like, how do I teach that? You know, how do I teach it? Not only being faced with the complexity, but also being faced with large language models nowadays, like Fable or Codex, where you just prompt what you want and you get a working program out of that. So how do you cope with the situation that students are no longer required to spend hours of debugging? Because that's where you actually learn a lot, you know. When you go with the debugger through this and finally you hit the bug, and then you say, I understand, you know. No longer required. So I think this is a big challenge for us to talk to each other and to come up with solutions. So far, I think it's very fractioned. It's very there is no real networking on this topic, even though everybody who is using C++ on the university is faced with the same challenge, is how to cope with large language models. And it's not going to be better.
Yeah, that's true. That's a road we're going to. Maybe not. We'll see. And yeah, so one of my takeaways from this event is maybe we get the professors to talk a bit more, at least those which are interested. And I said one of my goals is like to have 10, 15 professors in this, and we're at half point for that. So I think we're gonna get there. And then also we're going to have more students from various other places, and we are more able to compare what these folks do. And then we'll see where we go. I think the next event for this will be in September. So I, generally spend some time talking to the professors over summer, and then we'll see what date fits me to host this. And generally, I'm happy that everything went that well. And there's some lessons learned for next time, but fantastic event today. Thank you.
Thank you, Jens, for the invitation and organizing this. It's a big pleasure and a big opportunity to talk to each other and to get to know each other and really get the networking going. Thank you for that.
Yeah, I think it is like one important point. We're just getting started with this, so
exactly.
Thank you for everything. Right. And then we're now online for 2.5 hours live. So I was happy to fix my camera, so I can be here still without just But yeah, so thank you, Helmut. Thank you to all the other C++ professors, and then I guess we're going to do this again in September, and I'm looking forward to that already.
Me too. Okay, goodbye.